Good afternoon, and I welcome you all to this session. Last class we discussed the first law of thermodynamics. Last two consecutive classes we have completed the discussion on first law of thermodynamics applied to both closed and open system. Today we are going to start the discussion on second law of thermodynamics. The first part of the lecture I just request you not to take any note, you listen to it. This is the introduction to the second law. The second law of thermodynamics is probably the most important axiom or law of nature in physical science, in all branch of physical sciences. This is the law which puts a directional constraint or a unidirectional characteristics of all natural processes. Well, in the beginning of this class I told you that natural processes do not take place at random. There are certain rhythms or there is certain directional constraint or conditions for natural processes to occur, and it is the second law of thermodynamics which imposes this directional constraint. But these directional constraints are imposed in various forms on different natural processes. That is the reason that the second law are expressed in various forms, though they originate from the same basic concept of directional constraint. Just an example I am telling you, that if there are students from different branches, for example, there is a student of material science, there is a student of physics, there is a student of chemistry, there is a student of mechanical engineering, there is a student of chemical engineering, metallurgical engineering, energy engineering, and so on. This is a common experience, practical experience. If you ask what is second law of thermodynamics, you will see that everybody is answering in a different form, and all the answers are correct, which means the second law of thermodynamics is very wide and they can be expressed in various forms, but they originate from the same principle of directional constraint on natural processes. What is this directional constraint? We must understand before coming to some formal statements and its applications to certain aspects of engineering which is within the scope of this subject. So let me first tell you what is this directional constraint. Now let us start this way. We know that spontaneous natural processes always proceed towards equilibrium and take place in a particular direction. What is this? For example, liquid always or fluid always flows from a higher elevation to a lower elevation spontaneously. Heat always flows from high temperature to low temperature. Materials always diffuse from high concentration to low concentration spontaneously. Reverse of this never happen. If they have to happen, it has to happen with the aid of external energy or some external source. Without any source of external agency or without aided by any external source, these spontaneous processes take place in this direction only. Now come to another category of processes in nature aided by external agency. They also take place in one direction. Just for an example, a moving wheel can be brought to rest by the application of frictional brake, and by doing so the wheel and the brake gets hot. You can explain this from physical principle that kinetic energy is converted into intermolecular energy. But the reverse of this, that means to set this wheel in motion by cooling the wheel and the brake, is never possible by any external agent. Similar is the case that when you pass electric current through an electrical conductor or electrical wire, conducting wire, you see that wire becomes hot if it is insulated, its temperature is raised. But attainment of electrical work by cooling this conductive resistance can never be done. So there are a list of such processes aided by external sources also take place in one direction, but there are number of processes which are more in number in nature which take place in both the directions. So concept lies here. For example, you heat a body from a low temperature to a high temperature. You can cool a body from high temperature to low temperature. Heating and cooling both are possible. Well, you can expand a gas from a high pressure to a low pressure, and you can compress a gas from the low pressure to high pressure. While the gas is expanded from high pressure to low pressure, work is delivered. While you compress the gas from low pressure to high pressure, work is given to the gas. Similarly, we will see afterwards a heat engine can deliver work by interacting with two temperature levels, that it can take heat from a high temperature source, it can give heat to a low temperature sink. Similarly, a heat pump can be made to operate, which will take heat from a low temperature sink and will pump heat to a high temperature source. So, large classes of problems or processes in nature take place in both the directions, but here what is the directional constraint? That means these processes have a directional constraint. Like this, these processes are such that if they are executed in both the directions, then though the system comes back to the initial condition, the surrounding does not come back to an initial condition. Surrounding suffers a permanent change in a particular direction. This gives clue to the irreversible process, that I will tell you afterwards. So, therefore, we see that depending upon the class of problems, the directional constraint or unidirectional characteristics are imposed in various forms. That is why the thermodynamics second law have been evolved in various forms, which ultimately poses some directional constraint on the process, whatever may be the process. Some process may not be possible in reverse direction, some process may be possible in both forward and reverse direction, but put a constraint on the surroundings, that though this system comes back to initial state, surrounding fails to attain the initial state. So, this way the directional constraints are imposed in various forms, and the thermodynamics second laws are expressed in various forms. But in this class, we will be interested in understanding this second law of thermodynamics or directional constraints mainly from the engineering point of view in relation to energy conversion, and specifically in relation to conversion between heat and work, interchangeability between heat and work. These two types of energy in transit, that heat and work, interchangeability between heat and work. So, how we will start this? Now, let us see, before giving you any formal statement of second law in relation to interchangeability, heat and work, let us see that few definitions are required. Now, what is heat engine? Let us consider a heat engine. What is a heat engine? So, some definitions are important to know. Heat engine is a device. Heat engine is a device where a system operates in a cyclic process, so that it develops work when some heat is given to it. Do you see? You can see when some heat is being given to it. Let this heat is Q1. Now, heat engine is a device which operates on a thermodynamic cyclic process, whose output is the mechanical work and there is an input of heat. And to add heat, we have to have a system at some higher temperature. Let this temperature is T1. In this connection, we define the word thermal reservoir. What is the definition of thermal reservoir? Thermal reservoir is a system of infinite capacity such that when heat transfer takes place, either heat is taken from that reservoir or heat is given to the reservoir, its temperature remains invariant. That means it is a constant temperature, infinite capacity, heat capacity system, that is known as thermal reservoir. When the thermal reservoir is at a high temperature from where heat is being for that rejection, you have to have another thermal reservoir at a temperature T2, where T2 is less than T1, another thermal reservoir is known as sink, where heat is being temperature remains constant. To conceive a source T that means this is also true, but second law tells no, this is not true. So only this is the only solution. That means second law tells that you have only this as the solution. That means Q2 thermal efficiency. What is the definition of thermal efficiency? Eta H. This eta T, this is related to the heat engine. So thermal efficiency of a heat engine determines its effectiveness in converting heat into work. That means work is its output and this input heat Q1. And from the first law of thermodynamics, from the energy balance, we can write this Q1 minus Q2 by Q1, which becomes equal to 1 minus Q2 by Q1. So second law tells Q2 cannot be 0, even if the process is ideal. In absence of all friction, all dissipative effects, everything is ideal. Even in that case, Q2 cannot be equal to 0. That means the efficiency can never become equal to 1. That means a heat engine can never run even in an idealized condition with an efficiency equal to 1 or 100%. That means there has to be a rejection of heat. You cannot continuously convert the heat into an equal amount of work. This is precisely the first law of thermodynamics as expressed in terms of an heat engine as far as conversion of heat into work. This was first told by Kelvin, and the original statement actually came in a little different way, as I explained, because this is the easier way to understand the thing rather than first following the Kelvin-Planck statement like that. Now you can appreciate this statement, the Kelvin-Planck statement of the second law. It is impossible for a heat engine to produce net work in a complete cycle if it exchanges heat only with bodies at a single fixed temperature. That means it has to take heat and it has to reject heat, and for doing so we must have at least two temperature reservoirs, two distinct different temperature reservoirs, because from temperature reservoirs of a single fixed temperature you cannot perform these two processes. That means you can take heat but you cannot reject heat. So therefore Kelvin-Planck first put this statement in this fashion, that if it exchanges heat only with bodies at a single fixed temperature. Clear? Now you come to the next definition, that let us consider another system. Next statement of second, another form of this statement. Now you consider a another cyclic device known as heat pump. Known as heat pump. What is this? This, its work, its function is like that. Before that we should tell that if there is a temperature T2 and there is a temperature T1, and if T1 is greater than T2, we know that spontaneously, as I told, heat cannot flow from lower to higher temperature. It is a law of nature that we have found in nature. So this is another form of second law, that heat cannot continuously flow from lower temperature to higher temperature. But we can make a device like this. It is not a spontaneous process, but we can make a device which operates on a cyclic process such that it can take heat from low temperature and absorb work from surroundings and can deliver heat to the higher temperature. That means T1 greater than T2, same thing. That means pumping heat from lower to higher temperature is possible. not spontaneously, but we have to make some external arrangement, for which we have to operate a heat pump which will absorb work from surroundings. In this case, we can write from the first law of thermodynamics, conservation of energy, Q1 is equal to W plus Q2. That means this work is being converted into heat and by an equal amount. Here you see that heat is being pumped, but what is the underlying concept? That continuously this work form of energy transfer is now appearing in the form of heat. That means this Q1 heat which is being pumped to higher temperature, some part of it equals to the work W, amount of work W, which means that work can be continuously converted into heat. So therefore, I can write this thing now to tell you in a more clear way that if you convert heat in a cyclic process like this work, you always get work less than Q. But if you convert work in a cyclic process to get heat, work can be continuously converted. That means W is always less than, but Q is equal to W. Try to understand, not always it is the case, but you can never do it, but you can do it. Under this you can never do it under ideal conditions. Even under ideal conditions you cannot do it, but here you can do it under ideal conditions, that all the work can be continuously converted into heat, where all the heat cannot be continuously converted into work. Now here I tell you one very important thing which many people, even after reading thermodynamics many times, fail to understand, that this interchangeability heat into work, that a heat engine has to reject a heat. For example, this thing I tell you again, this is a very important concept, that a heat engine has to reject a heat even in the ideal case. That means its efficiency can never become 1. This is a restriction from the physical law that even an ideal machine cannot do, not from the practical constraints. For example, electrical motor can attain 100% efficiency. A mechanical transmission system, a fluid transmission system, or a generator, they can all attain 100% efficiency without barring any physical law, but they cannot attain because of practical constraint. You cannot get rid of dissipative effects, electrical resistivity, magnetic hysteresis, fluid friction, mechanical frictions, they prevent them from attaining 100% efficiency. But we can conceive of a frictionless transmission system, a frictionless fluid transmission or mechanical transmission system. We can consider a motor without any eddy current loss and having 100% efficiency. So from the viewpoint of physics, this is permissible. But in case of heat engine, even an ideal heat engine, in absence of friction or any dissipative effect, they can never attain 100% efficiency. That means this constraint or restriction of unattainability of 100% efficiency is even on the ideal case. That means this is a law of physics. This constraint is there on the law of physics. It is not because of natural constraint, because of dissipative effect. Even in the ideal case it does not happen. This is an axiom. This is the second law as far as the interchangeability heat and work is concerned. Again you see that continuous convertibility, heat into work, work is always less than it. Some heat has to be always rejected in converting it into work. But if you want to convert work into heat, we do not have to reject work. All work can equally be converted into heat. And this is the base by which we define heat as a low grade energy and work as a high grade energy, that I will come afterward. Before that, we go through another statement of second law, which is the Clausius statement. This statement tells that it is impossible to construct a device which operating in a cycle will produce no effect other than the transfer of heat from a cooler or to a hotter body. That means spontaneously heat cannot be transferred from a cooler body to hotter body without producing any other effect. That means it can be done by a heat pump if it takes work from the surrounding. That means there is an effect in the surrounding, that surrounding losing some work, surrounding has to give that work. This is another step. It is not very important to memorize this statement, just to know how this statement was first described by the scientist Clausius, by the scientist Kelvin and Planck. But their implicability, but how they are used, that is more important. Now after this I come to the definition of reversible process. Well, is a very important. What is a reversible process? Now we know by information that all we have told so many times that all natural processes are irreversible processes. Then what is a reversible process? Reversible process is that, so all processes are irreversible process, that is a directional law. That is also a second law. I told that all natural processes have a unidirectional characteristics, have a directional constant. What is that constant? That all processes are irreversible. So very apparently it seems that irreversible process means the process cannot be reversed back. And it is true for some processes which cannot be reversed back. I told you that conversion of mechanical energy intermolecular energy, I told it cannot be reversed back. Heating up an electrical wire by applying electrical work transfer cannot be reversed back. That means I cannot cool the wire and get the electrical work back. So these are very easily understood, but large classes of practical problem can be made to occur in both the directions. Then where is the definition of reversible process? A process is reversible. It's not that the process cannot be reversed back, but the definition is that if a process has to be reversible, that after the conclusion of the process, if by any means the system can be made to the original state without affecting the surrounding, then the process is reversible. That means if after the conclusion of the process by any means we can restore both the system and the surrounding at the initial conditions, then the process is reversible, which we cannot do for any natural processes. This is expressed in various ways. You can tell the language may be different, that after the conclusion of the process, if the system and surrounding is made to come back to the initial stage without any change in the rest of the universe, the process is known as reversible. Otherwise it is irreversible. Now let us understand how it happens in some natural processes as I have described, which can be caused to occur in both the directions. Consider heating of a body and cooling of a body. Very simple example. People always tell, sir, why it is not reversible process? I can heat a body from some temperature to a higher temperature, I can cool it. Yes, I will start with that. Let us consider a system which is at a temperature TA. Now let us heat it to a temperature TB. The same system, heat it to a temperature TB. Now TB is greater than TA. What we should do? Tell me. We should keep a hot body with a diathermic wall which will transfer heat Q, whose temperature Tc which will be greater than equal to TB. Otherwise it cannot be heated up to TB. So if you make equal to TB, then ultimately it will be a very slow process at the end, and slowly asymptotically it will reach the temperature TB. But in practice what happens, this Tc is much higher even than TB. So within a small time it is heated from TA to TB. Alright. Now if you cool it back again from TB to TA, it is permissible. We can do it. So what we have to do in that case? We will have to extract the heat, and where the heat will be rejected, that means we will have to consider another body from the surrounding with a diathermic wall so that heat can transfer, whose temperature Td has to be less than equal to TA. Clear? Now you see the system comes back to its initial state, but surrounding suffers a permanent change. Surrounding does not accept it. Why? Because you have taken Q from a high temperature body of the surrounding and you have given back the same Q to a low temperature body of the surrounding. That means if you want to make the surrounding to come back to the initial state, that means you will have to return this to this. For an example, let this is 20 degrees Celsius, just a numeric, it is 80 degrees Celsius. That means this temperature will be 80 degrees Celsius or more than that, and this temperature will be less than 20 degrees Celsius. So therefore we will have to give back the heat from 20 degrees Celsius to 80 degrees Celsius. It is not possible spontaneously. Then you have to use a heat pump which will again take work from the surrounding. That means without any change in the surrounding we cannot give it back, because this process is not spontaneous. So there is a permanent change in the surrounding. So heat is lost from one part of the surrounding, heat is gained in other part of the surrounding. You understand? That means if I take money from you and give it back to him, I think as I am concerned, I come to the initial state. I did not have money, I took the money, I have given back the money, but this classroom has not come to the initial state because money has come from him and has gone to him. So he has to give back the money to him. So this way you have to understand that heating process or a cooling process is a irreversible process. Consider the expansion and compression of a gas. Can you tell me why it is irreversible? Because I can expand a gas from certain pressure and temperature in a piston cylinder arrangement, for example, to some pressure and temperature, lower pressure and temperature. I can again compress back the gas to its initial pressure and temperature, in which way the surrounding suffers a permanent change. Can you tell? In doing so, can you tell? No heat exchange. I consider an adiabatic system. Adiabatic system takes some gas, you expand it. You understand that its temperature falls down. Then you compress the gas to a high temperature, no heat interactions. First I restrict the heat interactions. If he tells heat interaction, okay, he can explain through that. But even if we restrict the heat interactions, I can make some gas within a cylinder and piston, everything is insulated. I can expand from high temperature and pressure to a low temperature and pressure, and I can again compress. In which way the work done in these two processes will not be same. That means work obtained in one process will not be the same. If you measure the work, if you calculate theoretically through an ideal system or reversible process, they will be same. PdV work. PdV work is not the actual work. So the actual work requirement in compression is not the same as actual work obtained in the expansion process. Because of what? Because of the hysteresis due to mechanical dissipative effect friction. So these are the examples by which you can see that all natural processes which can be reversed back occurs in such a way that the surroundings suffers a permanent change, that surroundings cannot come back to the initial stage before the process, before the occurrence of the process. So this is the basic definition of reversible and irreversible process. With this in mind, now I write that therefore what is the causes of irreversibility. All natural processes are irreversible processes. So causes of irreversibility. Causes of, now I come to causes of, with this understanding, causes of irreversibilities. Causes of irreversibilities. There are two causes. One is lack of thermodynamic equilibrium. Lack of thermodynamic equilibrium. Well, lack of thermodynamic equilibrium. Now thermodynamic equilibrium consists of three equilibrium. One is mechanical equilibrium, one is mechanical equilibrium, well, one is mechanical equilibrium, mechanical equilibrium, mechanical equilibrium, another one is thermal equilibrium, very good, thermal equilibrium, and another one is, this we have already discussed, thermal equilibrium, and another one is chemical equilibrium, very good, chemical equilibrium. That means lack of any of these equilibrium, thermal equilibrium associated with dP, thermal equilibrium associated with dt, mechanical, and this is associated with concentration or chemical potential. This of course beyond the scope of your subject, chemical potential d mu c. So that means whenever a process occurs, there is always a lack of equilibrium. If work transfer has to take place, there will be a lack of pressure, that means mechanical equilibrium, lack of pressure equilibrium. There is a lack of temperature equilibrium, that is thermal equilibrium. There has to be a temperature difference for heat transfer to take place. Similarly, there has to be a concentration difference for a mass transfer process to take place, and there has to be a chemical potential difference for a chemical reaction to take place. But when all these equilibrium, that means all these things, dP is 0, dt is 0, dc is 0, that means all the equilibriums are established and there is perfect thermodynamic equilibrium and no process will occur. But whenever there is a natural process, there is a lack of thermodynamic equilibrium, because lack of thermodynamic equilibrium initiates the natural process, and this is one of the prime causes of irreversibility. Another causes of irreversibilities are dissipative effects. Dissipative effects. You know what are dissipative effects? There are different kinds of dissipative effects. Dissipative effects are always associated with all natural processes. What are those dissipative effects? Please tell me one or few. Friction, very good. Mechanical friction, very good. Mechanical friction. Please tell few other. Fluid viscosity, very good. Tell please. Fluid viscosity, I am happy. Please tell. Magnetic hysteresis, very good. Magnetic hysteresis. Then inelasticity, electrical resistance, so on. So there are large number of dissipative effects associated with natural processes. They are also causes of irreversibility, which means that if there is no lack of thermodynamic equilibrium and there is no dissipative effects, the process will be reversible. But for all natural processes, there have to be lack of thermodynamic equilibrium and there have to be dissipative effects. So therefore we can conclude that all natural processes are irreversible. This is because the basic requirements of the natural processes are the causes of irreversibility. Other way, the causes of irreversibilities lie in the basic requirement of a natural process. So therefore a perfect reversible process means there is no process. So we can only think of a limiting reversible process, then a reversible process in limit. So reversible process in limit, you can think this way, that process perfectly reversible or ideally reversible, perfectly reversible, reversible and reversible in the limit, reversible in the limit, what it will be? If it is a work transfer process, mechanical work transfer, I am sorry, mechanical work transfer, mechanical work transfer process, for a perfectly reversible dP is 0, there is no pressure gradient. Sorry, I will not write like that, I will write delta P is 0. In a reversible unit, so dP very small tending to 0 or delta P tending to 0, delta P tending to 0. Similarly for heat transfer process, delta T has to be 0, that is no process. Perfectly reversible means no process, because without a temperature difference heat cannot be transferred. But in the limiting case, when delta T tends to 0, that is a reversible process in the limit, reversible heat transfer process. Mass transfer process, mass transfer process, mass transfer process. You see that delta C is 0, there should not be any concentration gradient, but ironically without concentration gradient mass transfer is not possible. So therefore we think of a limiting reversible mass transfer process when the mass transfer takes place in infinite small concentration gradient. This means that infinite small gradients are there, that means dP, dt, that means work transfer is taking place with an infinite small difference of pressure dP. Heat transfer is taking place with an infinite small difference in temperature dt. Similarly, mass transfer is taking place with an infinite small concentration difference dC. All right. Similarly, chemical reaction. Similarly, chemical reaction delta mu Ci. This of course you don't know. So delta mu C, that is chemical potential which causes the reaction to take place. That means there will be an infinite small chemical potential. So therefore, for a reversible process this has to be 0 and in the limit this has to be, but for all of this one thing is obviously valid, no dissipative effect. That means on the top of it there should not be any dissipative effect, plus all these equilibrium should be established, that means no process. But in practice if you set this infinite small, usually this in turn related dissipative effects also will be 0. dissipative effect will be less, because if there is an work transfer with a small pressure difference, the process will be so slow that mechanical dissipative effects, the mechanical hysteresis will be less. Similarly, if you pass current to a infinite small against infinite small voltage difference, the electrical hysteresis, electrical dissipation will be less. This is the now the conclusion for the reversible process. Now let us take a very interesting one which will be important afterwards, a heat transfer process, a reversible heat transfer process. Just read reversible example of reversible heat transfer process. How do you conceive reversible? Just an example, reversible heat transfer process. Now you see a reversible heat transfer process. Let us consider a mass of water in a beaker, simple, at 20 degrees Celsius, and you want to heat it to 80 degrees Celsius. Just I give an example with numerical figure. I heat it by placing it with 100 degrees Celsius body. Let us take an arbitrary temperature 100 degree which is higher than this, so that in some finite time I get this result. Then what is happening? This is an reversible or irreversible heat transfer. This is an irreversible, because there is always the temperature gradient. If I take it at 80 degree, for example, okay, let us take, then if I draw the temperature versus time, tau is the time here. Now this is the source temperature remaining constant 100 degree. Let us consider this body is of infinite capacity whose temperature does not change. That means it is going like this. So initially 20 degrees Celsius, it is 80 degree. It is delta T. That means the degree of irreversibility ultimately is reduced at the end of this is the delta T. This causes the irreversibility. So degree of irreversibility is reduced at the end of the heating process. Okay, so this is a purely reversible heat transfer. As you want to make this process faster and faster, you have to make a more and more temperature gradient, so that process becomes more and more irreversible. So fastness of the process is that way related to the irreversibility. It is directly related. The more is the process fast, more is the irreversibility. But how do you conceive a reversible heat transfer? So same thing can be done if I consider this way, that if I consider number of reservoirs like that. One reservoir is 20.01 degrees Celsius. It may be still smaller resolution, just I gave an example. Instead of placing it directly to a reservoir of 100 degrees Celsius, I do like that 20.03 degrees Celsius, and this way I go, and ultimately I have also 3 reservoirs in this way. This is 79.97, 98, 79.99 and 70/80. And what we do, if we keep this system water here and we heat it from 20 degree to 20.01 degree with an infinite small temperature difference of 0.01, it will take infinite time, but this heat transfer is in the limit reversible. Then we place this where we heat this from 20.01 to 20.02 degrees Celsius. Again we keep it here. These are extremely slow process until its temperature 20.02 to 20.03 degrees Celsius is at. So this way, if we keep this, you will see that means here 79.97, because earlier reservoir it was 79.97 to 79.98 degree Celsius. Here also 79.98 degrees Celsius to 79.99 degrees Celsius, and finally here it will attain 79.99 to 80 degrees Celsius. So that this way, if we think of an infinite number of reservoirs with small temperature differences, and you always keep this system with all reservoirs for an infinite small amount of temperature rise, then we can conceive of a heat transfer process which is infinitely slow, but with a infinite small temperature gradient. So, that is in the limit a reversible heat transfer, which is very important. Afterwards in the analysis of cycle it will come how we can conceive and reversible heat transfer when the temperature of the system varies. Okay. So, with this I can conclude this understanding of reversible process, what are the causes of irreversibilities and under what condition a reversible process can be conceived, and actually that condition leads us that there should not be any process, but in the limit we can have a reversible process when the equilibrium is very, very small, that means a very infinite small departure from the equilibrium, thermodynamic equilibrium, and at the same time dissipative effects are small. Okay. Now, after this I will come to a very important statement of Carnot's. Before that, which is very important, I will tell what is the reversible heat engine. Reversible heat engine, reversible cycle, and obviously reversible heat engine. Obviously, by common sense one can define reversible cycle. Cycle means series of processes, so that initial state and final states are same. A reversible cycle is a cycle where all the processes are reversible. That means if any one of the processes becomes irreversible, the cycle is irreversible. And a heat engine or a heat pump, both operating on a reversible cycle, are called reversible heat engine or reversible heat pump. As simple as that. With this in mind, we will go to a very important theorem or corollary of the second law. This is probably the most important corollary of the second law. After that, the entropy will come, that is known as Carnot's theorem. He is the man who is the inventor of the second law, Carnot's theorem. No heat engine can be more efficient. Very careful, it is very important. No heat engine can be more efficient than a reversible engine operating between the same temperature limits. It may appear very simple, common sense, but it is not so. It has to be proved logically. He was the first man who proved it logically. Between the same temperature limits. What do you mean by temperature limits? The temperature of heat addition and temperature of heat rejection. That means, if you make the temperature of heat addition and temperature of heat rejection same, then if you operate a reversible engine and irreversible engine, reversible engine will always be having the higher efficiency than a irreversible or a natural engine. All natural engines are irreversible engines because all natural processes are irreversible processes. And at the same time, the second part of it, and all reversible heat engines operating between the same temperature limits have the same efficiency. All reversible engines operating between the same temperature limits have the same efficiency. What does it mean? Try to understand. That means, if the two temperatures are fixed and you operate different engines, but all reversible, their design is different, their fluid is different, that is system is different, working fluid or working system, but all are reversible heat engines, then they yield a unique efficiency. They yield a unique efficiency when the two temperature levels are fixed. So, all reversible heat engines yield an unique efficiency. But on the other hand, if you fix the same two temperature limits, and operate number of irreversible or natural heat engines, they will yield different efficiencies. That is the beauty. They will not all yield same efficiency, but even the maximum of these efficiencies is lower than the efficiency given by all reversible heat engines. You understand? That means, efficiency of all reversible heat engines will be the same, and that will impose a maximum value or the maximum value on the efficiency of all the irreversible engines, that all irreversible engines can never attain this value. Their values will be different, but their maximum also will not be equal to the efficiency of a reversible engine. This is the basic understanding of this Carnot's theorem. Let us prove this Carnot's theorem. Let us consider a source T1. Source you know, thermal reservoir at high temperature, which is fixed if we take heat of infinite capacity. Afterwards, now we, for our convenience we take a constant temperature source. Afterwards we will think that even if this temperature may vary, that means heat engine may interact with the bodies of finite capacities. That means heat is extracted, the temperature of the bodies, that is source, also changes. That will come afterwards. In that case the mean temperature of heat addition and rejection will come. But now we will assume that temperature of heat addition and rejection remains the same. That means the source and sink, they are by their literal meaning they are source. That means even if they transfer heat, their temperature remains the same. Even if they take heat, their temperature remains the same. We consider a heat engine. One is a reversible heat engine, HER. Well, this is the sink. Another one we consider an irreversible heat engine. I just designate as HE. And for this analysis, what we do, we just set the heat addition by the reversible engines and heat addition or heat taken by the irreversible engine are same. That means we put first this. For this proof, we first use this equation. That means as if they are taking the same heat. There is no problem in it, because we know that work delivered, heat added and heat rejected, out of these three, two are independent, one is automatically fixed. You understand? So out of these two I can set one Q1 for both the cases, heat addition to be same. In that case what will happen? This will be WR, this will be ordinary W, and heat rejected will be different because they are different engines. So if you keep this one, the efficiency will be different, so that heat rejected is Q2R for reversible engine or Q2 for ordinary engine. Now what we have to prove? We have to prove the efficiency, that is thermal efficiency of this is greater than what? This. This we have to prove. Now what is the definition of eta R? Please, that is W by Q1R. What is the definition for eta here? The same definition. What is the expression? I am sorry, what is the expression? W by Q. Well, so we have to prove that WR is greater than W. Okay. First we assume the reverse, that eta is greater than eta R. We assume this first. Now you see the concept lies here. Now we reverse the reversible heat engine. Very important concept. We can reverse the irreversible heat engine also and it will operate, because I told reverse direction a cycle can operate, a process can operate. But what is the difference? If it is a reversible cycle, it is a reversible process, if it is reversed, the surrounding will be the same. That means it will produce the exactly identical opposite effect to the surrounding. Similar is the case for the cycle also. That means if I reverse this one, then what will happen? Just let this is acting as a heat pump. Now I reverse this. That means this is the cycle, I reverse the cycle, use it to act as a heat pump. So what it will do? It will then in that case take the same heat Q2R and we will give the same heat Q1R, and it will demand the same WR. Why? Because it is a reversible cycle, reversible heat engine, so that surrounding coming to the same condition. That means the identically opposite effect it will give to the surrounding. As I told, if the expansion and compression, any of the processes could have been reversible, so in that case what will happen? Work given and work taken will be the same. Similar is the case. That means if we made this reversible heat engine to operate in a reverse direction as a heat pump, so it will take WR, it will take Q2R and it will deliver Q1R. Understand? That means we can tell this way, that for the same WR input and same Q2R taken from here, it will deliver the same Q1R. Alright. Now with this Q1R I can give to heat, because this heat engine wants Q1 which is equal to Q1R. So this source is redundant, is not required. That means this system here will act as a source. That means I can link this, because this Q1R which is elevated, that will be elevated, that will be given to this heat engine. That means the system of this heat engine will act as a source to this. where the heat high temperature reservoir heat will be given, and since I have assumed this eta greater than eta r means W greater than WR, that means I am getting an work which is more than this requirement, that means I can link this, and I get still an additional amount of work W minus WR. Well, again I am telling, if I reverse it back, then it will take WR amount of work to take Q2R from this sink and to deliver Q1R to this T1 temperature, T2 to T1. It requires the Q1 is equal to Q1R, that means I can link this to this so that this heat is given to this heat engine. Clear? When W is more than WR, a part of W can be given to this to drive this heat pump. Till then we are getting some work W minus WR, that means the equivalent system is a system which delivers continuous work by operating with a single fixed temperature, which is a violation of Kelvin-Planck statement. So it is not correct. That means this assumption is wrong. What is the last part? Because W is more than WR, because we have assumed eta is greater than eta r, which means W is greater than WR. That means some part of the W can be used to drive this. Try to understand logically. That means still W minus WR amount of work is available. That means the equivalent system is a system which develops work W minus WR by exchanging heat with only bodies at single fixed temperature. Clear? Clear? That means the eta cannot be greater than eta r. So what are the options? Eta r is greater than eta or eta r equal to eta. Now eta r cannot be equal to eta. If eta r equal to eta, that means what happens? These two engines are identical. That means this will be also a reversible engine. We start with the proposition that this is not same as that. This has to be different. There is the logic. So that mathematically only this solution is left, eta r is greater than eta. Therefore, the efficiency of a reversible engine is more than that of a irreversible engine. Any difficulty in understanding, please tell me. So final logic is that eta r is greater than eta. That means the efficiency of a reversible engine is more than that of an irreversible engine if they are working under the same temperature limits. Because these are the two same engine. If eta r equal to eta, that means Q1R, Q2R, Q1, Q2, and they give the same work. So interchangeability of heat and work are the same, then they are the identical machines.
So we can assume one is reversible, one is non-reversible.
The reversible engines and irreversible engines are different. You understand that if an engine gives the same work with the same addition of heat and accordingly the same rejection of heat, that means that the two engines are identical. That means one is a reversible, other one also has to be a reversible. You understand? This is the logic that you cannot, these two cannot be equal. That means this has to be different. Otherwise they are same. When you will prove the next class the same logic I will give, that the two reversible engines have the same efficiency. That if you reverse the one, this cannot be greater than this. You reverse the another one, this cannot be greater than that. It's clear? You think about it also. So it cannot be equal. It's a good question, I understand. If they two equal, there is no proof. That means we start with the identical engines which take same heat, develop the same work. Their efficiencies are same. You understand? That means this is basic assumption is that a irreversible engine and reversible engines are different engines, means that their thermal efficiencies are different. So only two possibilities are there, either greater than or less than. If they are equal, that means they are same. That means they are either irreversible engines or reversible engines. Okay? In case of two irreversible engines, they are identical engines giving the same efficiency. All right? Thank you.